Hello everyone. In the previous lectures, we had been discussing a number of different displacement potentials, ending with the complicated looking Popkovich-Neubel representation. Now the stated motivation was that this Popkovich-Neubel representation would help us in solving something very important in 3D elasticity, which is the Kelvin's problem. Now before we can actually launch into the Kelvin's problem, we need to discuss a couple of mathematical precursors. Okay, so the first mathematical precursor will be in relation to the Poisson's equation. And of course, the motivation for discussing this is that if you remember, in the Popkovich-Neubel representation, the whole idea was to reduce the problem to the solution of Poisson's equation. So it makes sense to discuss the solution of Poisson's equation in general. Please note that this discussion in relation to the Poisson's equation is very general, doesn't only relate to the solution of the Kelvin's problem. Wherever you have Poisson's equation, this discussion is relevant. Okay, so the general way we can represent a Poisson equation is like this. We have the Laplacian operator operating on some scalar, some vector, any tensor field, but to keep things specific and without complicating the notation too much, we'll just say that this Laplacian operator is operating on a vector. Okay, so but this could easily be a scalar, it could be a second order tensor, right? Now this thing is going to be equal to some function, some given function f. Okay, and this also is a vector. Now the question is, what is the solution of this? Without worrying about the boundary conditions or anything, we'll have to worry about the boundary conditions in relation to specific problems, but in general, do we have a solution for this? So the answer is yes, we do have a solution for this, at least the particular solution. So when I say particular solution, I basically mean it in the sense of when as first year engineering students, we studied the solution of differential equations. We studied them as composed of two parts, the homogeneous part and the particular integral of the particular solution. It is that particular solution I'm referring to here. So the particular solution to this Poisson's equation is given by this. The superscript p represents the particular solution, and this functional dependence on the x vector, it represents basically the notion how the particular solution will depend on the various positions that we are sitting at. Okay, so this thing is going to be equal to minus 1 by 4 pi integration over the entire volume of consideration small f vector. So this is this, so let me discuss what I mean here. Okay, so this is rather complicated looking, but let us just break it down. So see, this entire integration is taking place with respect to a dummy variable for the integration purpose, which is this x dash. Okay, there is a vector of course, but this is the prime variable. This is not this variable. This x vector is only present in the denominator here. Okay, you understand that this entire integration is with respect to this x dash vector. The cube here represents that this is basically a volume integral. Okay, so possibly some of you are more familiar with the representation that we put 3 integral signs here for a volume integral. If you want, you can do that. What I basically mean is that I am integrating this over the entire volume of concern. Okay. This x vector, it represents that whatever the result of this integration is, it will be a function of this x vector. Because after this integration with respect to the x dash has been done, please note that we know the form of this f vector because it is given to us. That is the load or the source driving the distribution of whatever this f has to be. So we know this. We can carry out this integration either analytically or numerically. Various methods are there, and we end up with a functional with an answer which depends solely on x dash. Okay, so sorry, on x vector, not on x dash, not on the x dash. So this is it. So this is the particular solution. Now the total solution, so the complete solution, it will be a summation of this particular solution and the homogeneous part. So the homogeneous part will correspond to the solution of this by putting this thing to be equal to 0. Okay, so FH is basically the solution to this part. Okay, whatever the solution of this is this. All right. So this is exactly following the notion that we learned in our first year engineering mathematics. Okay, now the immediate question is, how do we even arrive at this thing? Okay, so I'm not going to go into the details of this because that is almost a chapter in applied mathematics in itself, and we have to, let me just tell you that we have to go down the route of using something called the Green's function. There is an entire very mature theory associated with these green functions. For the purpose of our course on applied elasticity, we do not have to know those things. We only have to know that the particular solution comes out to be of this form. However, for those of you who are interested, you can just Google it, or I can maybe share some learning materials later on associated with Green's function. But I'm repeating, for the purpose of applied elasticity, we do not need to go down learning those green functions, the theory of those green functions. We just have to utilize this particular form. All right. The next thing that we need to know is something called the 3D Dirac Delta function. Okay, so you are all familiar with the Dirac Delta function. So although we refer to it as a function, it is actually a distribution, but with certain caveats, we can call it a function. Strictly speaking, it is not a function. So the 3D Dirac Delta. Now all of you are familiar with the simple Dirac Delta from our engineering mathematics. So if you have a thing like this delta x is defined in such a fashion that this is equal to 0 for all x which is not 0. Okay, and at x there is a spike. Okay, so I hope you all remember this from your undergraduate engineering mathematics. Now the only thing that we'll do here in connection with our discussion of the 3D Dirac Delta is to just make this dependence not on x but on an x vector. That's it. And we'll say that this is true for all x vector not equal to 0. And you understand that this is actually like a 0 vector. Now you have to understand this, that this is this kind of a discussion, it is pertinent, like whatever is present inside these brackets, as long as that is not equal to 0. For example, we could have a situation like this, that delta x vector minus xi vector. So in that case, this is going to be equal to 0 as long as our x is not equal to xi. You have to understand it in this fashion, and this will carry a lot of importance in our subsequent discussions. Now, these are two apparently unrelated things, but you understand that we are discussing these in connection or as mathematical precursors to the Kelvin's problem. So what I will do is I'll discuss an example of a Poisson's equation involving this kind of a 3D Dirac delta. So let me do this in the next page. Okay, so suppose so you consider this kind of a Poisson's equation. Okay, so instead of the f as the small f vector which was present in the general theory in the earlier page, we have made it to be like this, where this a vector is some constant. Okay, it has three components, but it's a constant vector. Okay, it's not dependent on x or anything. Okay, now we also must understand that this xi vector, it is the position vector of a certain fixed point in space. Okay, so this xi vector is the position vector of a fixed point in space, or of a fixed point. Okay, so the particular solution to this, okay, the particular solution to this is given by, so let us check in the previous page what we had written. There was a minus 1 by 4 pi here. Okay, so this minus 1 by 4 pi, we'll write it exactly in this fashion, only replacing this f vector x dash by what we have in the present case. So this is minus 1 by 4 pi, just substituting the f vector by this thing. And please note that when we had written this equation, we basically meant it that this f was dependent on the x vector and this f was dependent on the x vector. Okay, so we replace that x vector by the dummy index here, by the dummy variable here, x dash. So that's exactly the same thing we are going to do here. So whatever was x in the original equation, we are going to replace it by this x dash. The xi is the position vector of a specific point, we don't touch it. And in the denominator, you note that we had written it like x vector minus x vector dash. So this x vector is the x vector that is relevant to the original equation, and this is the dummy variable that we have introduced. So this denominator, it simply does not change. Okay, there is no story of this xi here. And we have to finish it up by writing it properly, that the integration is with respect to the x dash. Now as we have already mentioned, this a vector is some constant, so it can very well come out of the integration. Now we are left with this thing inside. Now what do we do? Well, we can go back to this discussion of the Dirac delta and write a special property of this Dirac delta. So just like in our previous discussion of the Kronecker delta, we had mentioned that it has this very special power which you have come across so often, you use so often in your in the solutions of various problems and proofs, the substitution power. So also this kind of a Dirac delta has something which can be referred to as the filtering property. So suppose you have a situation like this, that you have a vector t and we have an integration like this, suppose. So this is x dash and we have the Dirac delta like this. Or we can use this to be some other variable, doesn't matter. Let's say this is anything else. Let's say this is a xi. And suppose again we are integrating over the entire volume, the x dash being the dummy variable for the integration purpose, and we are carrying out this integration. So what is the result of this? Now this is quite complicated looking, but the good news is, because of this filtering property, this has a very simple result, that this is simply this. Okay, so I believe some of you will be able to relate this thing with what you studied in connection with the one-dimensional Dirac delta which you learned in your undergraduate engineering mathematics. One very important point to note here is that for this formula to hold, you must ensure that this xi is lying very much within the volume. Okay, so this is true only if xi is lying within the volume of concern. So if we are carrying out this integration over a certain volume, this xi point must lie within the volume. If it is outside the volume, then this result is equal to 0. And there is this very special case that if suppose this xi is lying on the volume, on the surface of this volume, then you'll have to write this with a half. Okay, so that's just how this definition works. But for our present purposes, we don't need all of those things. We only need the case where xi is very much lying within the volume and the result is like this. Now you compare this thing, so this general result from this filtering property of the Dirac delta with what we have here. So let me keep that thing at the top of the screen. So you just compare. So we again have an integration. So this is a integration over a certain volume. And you note that just like we had this Dirac delta, this 3D Dirac delta with the x dash minus xi, so also we have this thing. Okay, and this t vector x dash, that is present here. So this is like a 1 by x magnitude of x minus x dash that is present here. And the only thing that happened was that whatever was present in the form of this x dash, that got substituted by this very specific point. So the exact same thing is going to happen here. So the result of this thing will be simply that the Dirac delta, it will unleash its filtering property on this function 1 by magnitude of x vector minus x vector dash, and we will end up with 1 by x vector minus xi vector. Please note that this should make sense to you, because this thing here is a function of x vector. Okay, so this right hand side also is a function of x vector, because you see this a vector is a constant, 4 pi is of course just a constant thing. The xi vector, it is a vector no doubt, but it's a very specific point. Okay, you're choosing a certain point, so this does not have any dependence on x. So this is the only dependence on x. So the right hand side is a function of x, the left hand side, as you are expecting, it should be a function of x. So it's all nice and consistent, and this is the answer to the particular solution. Okay, so there will be a different story associated with the homogeneous part of this equation, and it will have connections with what boundary conditions are relevant for that particular problem. But you'll see that when we actually start our discussion of the actual solution of the Kelvin's problem, this particular example that we have seen here, just as an application of what we were discussing in the previous page, it will become immediately relevant. So on that note, I will end this lecture here. Thank you very much.